Welcome to The Explainer. So today we're going to tackle a huge problem, one that comes up everywhere. How do you make an accurate guess when you just don't have all the information? I mean, think about it. Whether you're looking at election polls, reading about medical trials, or trying to figure out how well a product works, you're almost always dealing with just a small sample of a much, much bigger picture. We're going to break down one of the most powerful tools in all of statistics, the confidence interval, and see how we can go from making a simple, single guess to expressing our estimates with a level of certainty that's incredibly useful out there in the real world. All right, let's kick things off with a super simple problem. Let's say you need to estimate something. It could be anything, really. The average salary for a job in your city or the number of jelly beans in one of those giant jars. Your first instinct, our totally natural human instinct, is to just blurt out one number, but just stop and think about that for a second. If you guess there are exactly 3,452 jelly beans in that jar, what are the chances you are exactly right? Pretty much zero, right? A single guess is incredibly precise, but that precision is actually its biggest weakness. It's almost guaranteed to be wrong. And check this out. This slide lays it out perfectly. On the left, you've got your point estimate. Saying the temperature will be exactly 35 degrees, well, that's a really fragile guess. If it hits 35.1, you're wrong. 34.9, wrong again. But more than that, it's not very helpful for making decisions. Now look at the right side, the interval estimate. Saying it'll be between 30 and 40 degrees gives us a way more useful and reliable range. It admits that, hey, there's some uncertainty here, and it gives us a plausible window for the truth. This range lets us make a smart decision. We know it's going to be a hot day, so we can plan for it. This is the big shift in thinking we're exploring today, moving away from a single, likely wrong number to defining a useful, probable range. So here's what's on deck for today. We've just talked about the problem with using just one number. Next up, we'll figure out what makes a good starting guess in the first place. Then we'll build up the main idea of a confident range, and we are going to decode the formula that makes it all work, piece by piece. After that, we'll see it in action with a real example, and then finally, we'll wrap it all up and talk about why this is such an important idea to get your head around in our data-filled world. Okay, so before we can even think about building that reliable range, we gotta have a solid starting point, a trustworthy guide. In the world of stats, the formula or method we use to make that first guess from our sample data is called an estimator. You can just think of it as the recipe we're gonna follow. So let's see what makes for a good recipe. So what is an estimator? Well, think of it as just the tool or the formula that we use. And the thing it's trying to estimate, that's called a parameter. A parameter is some number that describes a whole population, like the true average height of every single person in a country. We use that Greek letter mu, for the population mean. Now, since there's no way we can measure everyone, we take a sample, right? And we calculate a statistic from that sample, like the average height of the people we actually did measure. We call that sample mean X bar. So in this case, X bar is our estimator. We use it to make an educated guess about mu. And that's the whole game right there, using the thing we can calculate, our statistic, to learn about the thing we can't, the parameter. Okay, and this is where it gets really cool, because not all recipes, not all estimators are built the same. A good one has two really key qualities. First, it has to be unbiased. So imagine you're an archer. Being unbiased means that if you shoot, say, 100 arrows, they might not all hit the dead center, but the average position of all those arrows is the bullseye. Your aim is fundamentally good, even if you're not perfect every time. Second, a good estimator is efficient. In our archery analogy, this means your arrows are all bunched up, tightly clustered together. You don't just hit the bullseye on average, your shots are consistent. I mean, who would you want on your team? The archer who's all over the place, or the one whose shots are tightly packed right around the bullseye? It's a no-brainer. In statistics, the sample mean, our friend X bar, is a fantastic estimator because it's both. All right, so we've got our good starting point, our trusty, unbiased, and efficient estimator, the sample mean. Now let's see how we actually build out from that single point into the main event, the confidence interval itself. And here it is. This right here is the solution to that whole single guess problem we started with. A confidence interval gives us a range of believable values for that unknown population parameter we're hunting for. So instead of just saying, our best guess is X, it says, hey, based on our sample, we're pretty sure the true value is somewhere between X minus a little and X plus a little. It gives us a floor and a ceiling, creating this nice window where the truth probably lives. Okay, but here's the thing. That range always comes with something called a confidence level. And honestly, this is the one thing almost everyone gets wrong, so let's really nail it down. The confidence level, usually something like 90%, 95%, or 99%, does not tell you the probability that the true value is inside your specific interval. That's the trap. The true value is what it is. It's either in the range you calculated or it isn't. The confidence is in the method. It's a statement about the long-term success rate of the recipe you used. So let's really hammer this home. What does a 95% confidence level actually mean? It means this. If we were to do our whole experiment over again, say 100 times, we go out, we get 100 different samples, and for each one we build a 95% confidence interval, we would expect that 95 of those 100 little windows we built would successfully capture the true unknown value. The other 5, they'd miss it. Not because we did anything wrong, but just due to the random luck of a draw. Our confidence is in the reliability of our procedure, not in any single result. Okay, deep breaths, everyone. We're about to look at the formula. I know, it can look a little scary with all the symbols, but I promise we're going to take it piece by tiny piece, and it's going to make total intuitive sense. Let's decode the engine that builds these intervals. You know, when you really look at it, the core idea here is super simple. It's just our point estimate, that's our single best guess, and then we add and subtract a margin of error. That's it. We start with our best guess, and we build in some wiggle room. The entire rest of that formula is just a very precise statistical way of figuring out exactly how much wiggle room we need. So let's see what goes into calculating that wiggle room. First piece of the puzzle, X-bar. And hey, we already know this guy, right? This is our sample mean, our unbiased and efficient estimator. It's the single number we crunched from our data, and it acts as the center point, the anchor for our entire interval. Everything we do from here is built around this one best guess. All right, next up is this Z thing. I love calling this the confidence multiplier because that's exactly what it does. It's the part of the formula that dials in how confident we want to be. This number comes from the classic bell curve, what statisticians call the standard normal distribution. All a Z-score really tells you is how many standard deviations away from the center you are. So a bigger Z-score means we go further out from the center, which naturally creates a wider interval, giving us more confidence. And this table here, it connects all those dots for us. Let's just walk through the most common one, the 95% level, together. If we want to be 95% confident, that means we're willing to accept a 5% chance of being wrong. That 5% is our alpha. Now, since our interval has two ends, a high end and a low end, we split that risk of error between the two tails of the bell curve. So we put half of alpha, 2.5%, in each tail. The z-value that cuts off that top 2.5% is 1.96. That's where that famous number comes from. Want to be 99% confident? Well, your risk, alpha, is only 1%. You put 0.5% in each tail, which means you have to go way further out on the curve to a z-value of 2.58 to capture that big chunk in the middle. Okay, last piece of the wiggle room calculation. This part is called the standard error. It's basically a measure of the uncertainty that's baked into our sample mean. It has two ingredients. First, there's sigma, the population standard deviation. This just tells us how spread out the original population is. If everyone's pretty much the same height, any sample you take is going to be pretty close to the truth. But if heights are all over the place, there's more uncertainty. The second ingredient is n, our sample size. And notice where it is. It's in the denominator under the square root sign. This is huge. As our sample size n gets bigger, the standard error gets smaller. That makes total sense, right? More data, more certainty. So you take that confidence multiplier, the z-value, and you multiply it by our uncertainty measure, the standard error, and boom, you get the whole shebang, the margin of error. This is the total amount of wiggle room we need. It's the total plus or minus part that we tack on to our best guess. And it all comes from two simple ideas. How confident do we want to be, and how much uncertainty is naturally in our sample? Okay, theory time is over. We've built the engine, we know what all the parts do, now let's take this thing for a spin with a real-world example and see how it all clicks together. All right, so I want you to picture this. You're a quality control engineer at a factory that's pumping out thousands of these little electronic circuits. You need to estimate the true average electrical resistance for the entire production run, but there's no way you can test them all. So you grab a random sample of 11 circuits. You test them and you calculate a sample mean resistance, our X bar, of 2.20 ohms. Now, from years of data, you know the population standard deviation, sigma, is a steady 0.35 ohms. The mission? Construct a 95% confidence interval for the true mean resistance of all those thousands of circuits. All right, let's just plug and chug. We'll follow the steps right on the screen. Step 1, we need our z-value. We want 95% confidence, so we already know our z-value is 1.96.
Easy enough. Step 2, let's calculate the standard error. That's sigma, which is 0.35, divided by the square root of our sample size, 11. The square root of 11 is about 3.317, so 0.35 divided by that gives us a standard error of about 0.1055. Step 3, now we get the full margin of error. We just multiply our z-value from step 1 by the standard error from step 2. So 1.96 times 0.1055, and that gives us about 0.2068. And finally, step 4, we build the interval. We take our best guess, 2.20, and we plus and minus our margin of error.
And there we have it, our final interval, from about 199 ohms up to 2.41 ohms. But hang on, getting the numbers is only half the battle. The most important part is saying what it means in the right way. That phrase, "we are 95% confident," is very specific. It's pointing back to our confidence in the method we used. We are not saying there's a 95% probability the true mean resistance is in this one specific range. The true mean is some fixed number out there. It's our interval, which is based on a random sample. That's the thing that's random. Our confidence is in the procedure, a procedure that, if we did it over and over again, would successfully trap that true mean 95% of the time.
So we've been deep in the weeds with formulas and numbers and circuits. Let's pull back for a second. Let's zoom out and ask the big question, why? Why does any of this actually matter outside of a textbook or a classroom?
The truth is, in pretty much every field you can imagine, science, business, medicine, policy, we are always working with incomplete information. We have to make big decisions based on samples. A single number, a point estimate, it hides all the uncertainty. It gives you this false sense of precision. A confidence interval does the opposite. It brings that uncertainty right out into the daylight for everyone to see. Think about it. When a drug company reports the effectiveness of a new treatment, they use a confidence interval to show the plausible range of how well it works. When pollsters report a candidate's level of support, that margin of error they talk about, that's the heart of a confidence interval. It's the language of scientific honesty. It's an incredibly powerful way to say what we know, and just as important, to admit the limits of what we know. It gives people a realistic range, which is infinitely more valuable than a single number that's almost certainly wrong. So the question I want to leave you with is this. What's that one thing in your world, in your job, where a single number just isn't cutting it, where understanding the uncertainty could change everything?